Hello and welcome. I am Basim Mudassir, and I am going to be presenting an analysis of a power grid, specifically the IEEE 14 bus system. The objective of the analysis is to simulate a power grid under both stressed and unstressed conditions. We are going to identify the issues in the stress condition, and we are going to find an engineering solution to avoid those issues or improve upon their effects. So today we are going to be discussing the base case, the stress case, and how are we going to improve the voltage in two methods. And then we are going to come to a conclusion about which method is better. So stay tuned. So let's look at the system's overview. This system consists of 5 generators. These 5 generators can be actual turbines or they can be synchronous machines being operated as condensers, as that is the standard practice nowadays. Also, we have 11 loads, and we are considering the nominal voltage to be 132 kilovolt. This is actually a very good topology to test the voltage drops over long transmission lines. This is because this system has both generation heavy areas and also remote load centers. So it covers all the bases for the test. Looking at the analysis of the base case, we are trying to identify any low voltage buses. Looking at that chart, you can see that there are no actual low voltage buses. The lowest one I think is bus number 3, which is a little bit more over the 1 per unit value, which is still good result. Also, in the line loading analysis of the base case, we noticed that most of the lines are actually within limits, meaning that they do not exceed the 100% of the load, except for one, which is the line going from bus 1 to bus 2, which is overloaded. It has a 156% load, as you can see in the chart. This is a very critical problem. We will see how this analysis is going to be like when the system is actually stressed, not just a base case. Okay, now to simulate the stress case, we multiply the load by 1.5, meaning we are increasing the load by 50%. Then we do an analysis of the voltage profile of all the buses. We still see that no buses drop below the threshold to be considered an actual low voltage bus. But we are still going to target one of the lowest bus to be a subject for the improvement. We are taking bus 14 because it's the lowest bus. But before that, let's look at the load lining at the stress case. Okay, now looking at the line loading at the stressed condition, we see that not only do we have a single stressed line, but we actually have three lines that are being stressed. And these lines are the previous one, which is from bus 1 to bus 2. Then we have from bus 1 to bus 5, and from bus 2 to bus 3. These lines are loaded beyond 100%. This confirms that the system cannot effectively transfer the power to the generator. So this will be the subject of our trial for improvement. Okay, now that we have identified bus 14 as the weakest link in the system because it has the least voltage, we are now going to be trying to raise its voltage by 5%, effectively giving it more of a margin of safety. So the first method we are going to be implementing is the shunt capacitor. This effectively just adds reactive power at the bus to actually compensate for the losses that is happening at the bus. This method is going to be competing against another method, which is changing the voltage set points at the generators, because we are going to be asking the generators to generate more voltage to compensate for that losses. After we implement those two methods, we are going to have a discussion and compare them both. Okay, for method one, we actually simulated the installation of a capacitors bank at the bus itself. And through iterative simulation, we determined that we require 22 MVAR of capacitance to actually achieve that 5% of raise. And we tried that and we actually did achieve a 5% raise at the bus. So this actually demonstrates that we can actually improve the performance of a single bus using this method without affecting changes system-wise. For method 2, which is changing the generator set points through iterative simulation, we determined that we only need to increase the set points by 4.5 to actually get the increase of 5% or more at the voltage of the bus. But the difference is that this improvement actually happens system-wise, as we will see in the next section, which is the comparison between the two methods. Comparing both methods, we see that both methods successfully raise the voltage at the bus, but there is a difference in the performance of the system in both cases. In method 1, the total system's losses has been reduced to 33.8 megawatt. However, method 2 actually dropped it even further and significantly down to 30.7 megawatt. This is saving 3 megawatts. Looking at the reason behind that, it's actually because we are raising the voltage at the generator and keeping the load demand constant. That means the reduction has to come out at the current expense. And even a small drop in the current can create a massive reduction in the wasted energy. Project conclusions. Looking at the system as a whole, it's very robust, but its vulnerabilities actually occur at remote buses that has a deficit in reactive power. Also, we demonstrated that to fix this issue, we can use localized fixes like the shunt capacitors, or we can use a system-wide stability fix that is done by actually increasing the set points at the generator. But that's still not overlooking the major issue in line 1, 2. So my recommendation is to actually upgrade line 1, 2 to handle more load. That's it, and thank you for hearing my analysis.